Welcome back everyone to this lecture on image filters. Before we dive deeper into convolutional neural networks, let's first discuss a few key ideas in computer vision that pertain to the architecture of the way a CNN works. And keep in mind, computer vision is just a general term of using computer programs to process image data. And topics like image filters and image kernels, that's going to fall under computer vision. So let's try to understand some of these key ideas, and then later on we'll see how they relate to convolutional neural networks. Now, if you've ever used photo editing software or even photo applications on your phone, you've probably already seen filters, such as a blur filter. But the question arises, how do these filters actually work? What are they doing to the underlying pixels of an image in order to achieve this desired effect? Filters are essentially an image kernel. And keep in mind, the term image filter and image kernel can be used interchangeably. So you'll see some people just call them image filters and other people call them image kernels. The main idea is if you're referring to an image kernel, you're probably referring to the more mathematical understanding behind what the image filter is doing. So let's talk about that. So that image kernel, it's a small matrix applied to an entire image. Now, certain popular filters are actually well known. For example, to blur an image, you can actually just use this image kernel that I've shown here. This 3x3 matrix, when applied to an entire image, will actually blur the image. So let's get an idea of what we mean by applied to an entire image. So let's explore what that actually means to apply a kernel or filter to an image. Filters essentially allow us to transform images. So here we have a grayscale image. It's a really small image, and what we have are values that are scaled between -1 and 1. Where 1 represents black and -1 represents white, and then the value right in between them, such as 0, is essentially gray. So we have these normalized values between -1 and 1. And what I'm going to do is I'm going to apply a filter to this image. So here we have an example of a 3x3 filter. So what we're going to do here in order to apply the filter to the image is, starting at that top left, I'm going to see essentially the corresponding values to the filter. So essentially put that filter on top of those image pixels, and then we're going to begin sliding it along. And when we have the filter on top of the image, what we do is we multiply those pixel values by what we are going to refer to now as the filter weights. So the actual values of the filter, we're going to begin referring to them as weights because later on the convolutional neural network is going to choose those weights for us. But we've kind of predetermined some sort of filter values here in this 3x3 filter. So we take that filter, put it on top of our image, and then as we kind of scan across this image, what we're going to do is multiply by the filter weights. We get those results, and then we sum the result to get some final output value. So in this case, if we took that 3x3 filter just on the top left corner, multiply by those filter weights, and then sum those results. And notice how, in this case, the resolution will actually decrease because we're taking in 9 input values and then just outputting 1 value. Now, as I mentioned, we're eventually going to do this across the entire image. So we're essentially going to stride across the image. Now, something we can edit is our stride distance. So by default, we have to at least stride 1 pixel over, but what we could do is have a stride distance that's larger. Maybe we could stride over by 2 pixels. And that's something we can edit in our convolutional neural networks as well. So to get a better idea of how this actually works, there's a really fantastic interactive example that I'm going to go to now in my browser. And it's at this URL, satosa.io/ev/image-kernels. Okay, let's go ahead and go to this in our browser so we can get an idea of how these image filters are actually applied and what the resulting image looks like. Okay, so here we are at this satosa.io link for image kernels. And the explanation begins by showing you just a normal image. So often images have values that go from 0 to 255, where 0 is the darkest possible value and then 255 is the brightest possible value. So in the case of a grayscale image, we have 0 as black and then 255 as white. So we can see here that as we kind of hover above these values, we can see over in this white section that I'm currently hovering over, we get values that are pretty close to 255, and then maybe over here where it's darker, they're a lot lower in value, kind of in the 20s. Okay, so this is kind of a blown up, low resolution image. If you look over here on the very right hand side, you see this tiny little picture of of a face, excuse me, that's the actual kind of real size of this image. It's not blown up to this kind of larger scale, but what's nice about this larger scale is you can see each pixel very clearly individually. All right, so we have the numbers between 0 and 255, and what we're going to do is we're going to walk through the process of applying a kernel to this image. So here you can actually choose what kind of kernel you want to apply. We're going to begin with that blur kernel that we actually mentioned before. So here are 9 values, a 3x3 matrix or a 3x3 kernel that we're actually going to apply to this image in order to blur the image. So what ends up happening, and you can see this, you can play around with this interactively. Here, now we see that little 3x3 grid that we're going to end up applying across the image. And then you can see the output along with the math of the multiplication. And notice that the input image versus the output image. We can clearly see that the output image has been blurred due to the transformation of applying this kernel across. And this process of applying this kernel is sometimes also known as a convolution. The process of taking this image kernel and then dragging it or with a stride across this image and getting this output result. The term convolution is what we call this when we are talking about this in the context of a convolutional neural network. And the main idea behind this is, so far, we've actually shown you how these kernels or filters work with predetermined values. And those are values that are well known for certain really common operations like blurring an image. Later on, we're going to want our network to actually choose the weights behind these filters in order to perform feature extraction. Maybe we'll have some filters that are really good at detecting eyebrows or something like that if we're trying to classify faces, for example, from other images. So the main idea behind this image kernel in the context of a convolutional neural network is that the actual network will figure out the correct weights instead of us having these predetermined weights. And often, when you're working with a convolutional neural network, you'll get a lot of edge detection. And so we actually have some edge detection or Sobel filters here. And you can see here that this is kind of detecting horizontal lines. And you can even have an intuition of this by just checking out the matrix that we have these larger negative values here, and then a center 0 line, and then larger positive values on the bottom. And if you have an intuition of how this will react as you kind of go along the image, where you have strong vertical lines, such as this person's hairline here, you'll end up results that have larger values as you go along. So you can see here, because we're starting to detect these kind of horizontal lines, the actual output when you apply this kernel, just mathematically the way it works out, is very bright, versus where there are no horizontal lines, you just end up getting kind of black. So here we can see the output image is clearly outputting clear portions that are horizontal lines. So that's what's called the bottom Sobel. And then you can check out things like right, and it looks very similar, except now this should be detecting kind of vertical lines. So same idea here, we can now see clearly the vertical lines of this person's face on the left-hand side and this person's face towards the right-hand side. And we can also see their nose starting to appear in that output image. So the convolutional neural network is essentially then going to decide what weights on its own filters matter for image classification. And here we can actually have an interactive image and kernel uploader. So you can choose your own image file and then apply any of these kernels you want. And you can even develop your own custom kernels here. So it allows you to start editing these to do things that you want to explore. Okay, so the main idea here behind this website and showing you how it works is just get the idea that we're going to have these kernels. They don't need to be 3x3. They can be 4x4, 5x5. Obviously, the larger there are, the more operations and more weights we have to solve for. But we essentially just drag them over the image, and then it's going to output some sort of result. And hopefully, as the convolutional neural networks learn based off the images we feed it, we'll get certain outputs that are basically extracting important features. So here we're extracting edge features based off this kernel right here. And you can see here that we have an outline where essentially we're looking for the center value of 8 as our main center weight versus -1 on the edge. Okay, so let me go back to our presentation and finish off our discussion on image kernels. All right, I hope you enjoyed that interactive example, and I encourage you to explore that website on your own. Now, in the context, as I mentioned, of convolutional neural networks, these filters are referred to as convolution kernels, and that process of passing them over an image is known as a convolution. I want to go over a few more key important factors to keep in mind as we learn more about convolutional neural networks and image kernels. Now, during convolution, we would actually lose borders. So if you take a closer look at that previous example, you'll notice that there was a black border along the output image. And this is because as you start going towards the edge of an image, you'll actually end up just not having values there. So one way to fix this is you can pad the image with more values. And a really common choice is just 0, or a kind of in-between value. And this allows us to then not lose information along that border. So it also helps us preserve the image size. So this is known as padding, and it's a really common technique people often use on their images so they don't lose any border information. Okay, so now that we understand image filters, let's go ahead and explore the architecture of a convolutional neural network that allows the network to come up with the best weights for a filter in what is known as the convolutional layer. So we understand we have these image filters, or kernels, that we're essentially going to perform a convolution on the image. And I showed you filters where we already knew the weights for them. However, when it comes to images such as images of dogs or cats, we're not really going to know right off the bat what filter values or weights are going to be important in order to detect whether a dog is in an image or a cat is in an image. It's probably a better idea to just have the convolutional neural network to come up with those weights themselves. And this is done in the convolutional layer of a convolutional neural network, which we're going to go over in the very next lecture. I'll see you there.